This is a further maths paper, Core Pure Paper 2 from 2020 from the Pearson Green Butterfly books here, because I can never remember the names of anything, so it's just these books here that this is testing. 1.5 hours, you're given a calculator because of course you are. It's great, isn't it? Anyway, exact coordinates of stationary points of C. So stationary points mean dy by x is 0. Sine differentiates to cosh, so we can just differentiate that straight down. This 2 goes over to there to make a 4, and that's all fine. We can set this as 0, but of course you probably want to deal with this 2x here, because I don't really like that. The formula book just tells you that this thing is equal to this thing, so I'll replace that with that. Then I expand out, but also actually I can now replace this. I kind of just want stuff in terms of cosh maybe. So let's replace this with, I mean this is the formula again from the book. So we can just do sine squared is 1 minus cosh, sorry, it's cosh minus 1, it's cosh squared minus 1. So we get this, I believe, if you put that into there. Then you expand that out, you get this. We set that to 0 because we're looking for stationary points. You can times by minus 1 here just to make it looking a little bit more normal. This does factorize. Of course, you could just do a substitution and put it in your calculator, but it does factorize because 31 is quite close to 32, which gives you a hint that it's going to be this. I think you can double check it for me, which either means cosh of x is 0, sorry, cosh of x is 4, or cosh of x is minus an eighth. Now, cosh of x can't be a negative, so that doesn't happen there. This one here, again, one more time, the formula book tells you that this is arc cosh here. This is the formula that you can use. So we're looking for arc cosh of 4, of course, so we just need to put in 4 into here, and we'll get that answer there. Except we can also have a plus or a minus this. And there's a couple of ways of knowing that. Either you could have not just used the formula from the book, and you could have done the exponential definition of cos and solved, and you'll end up with plus or minus this. Or you could just think about the graph of cosh of x if you just know the graph of it, because if you're looking for when cosh of x is 4, so when is it 4? Well, it's on either side symmetrically, so you get both of these two things here. So yeah, cool. That's the first question done. The second one then, so we've got convex numbers here and here are the diameters of a circle. That of course means that the midpoint of this and this is the center. Midpoint of minus 3 and 5 is, I believe, 1 for either side, and midpoint of 2 and minus 4 is minus 1. So that's the midpoint, and the radius is, well, the distance between the x-coordinate of that and that is 4, and the y-coordinate essentially is what I'm thinking of right here is 3 from minus I to plus 2. So the radius is just going to be 5, 3, 4, 5 triangle. So we've got a circle which we can call, well, in this form we can just say it's z minus the center point, 1 minus I, in brackets of course, because it's minus the entire center point, not just minus the first bit. And then the radius is 5, so distance from z to the center point is always 5, is what this is saying. Now in the second part they're giving you another circle defined in the same way, but it's actually much easier to just think of this in terms of Cartesian coordinates and Cartesian forms of circles. So if we just completely ignore the complex numbers thing for the next few minutes, this is center 1 minus 1, right? Radius 5, so that's actually a circle that looks like this in Cartesian form. And here, just be careful, they've written this in a bad form. You should have minus brackets. So I'll just put this in brackets and swap that sign. But again, this is just a circle with radius 2, center minus 2, minus 3. So I think I need to write it, sorry, center 2, 3. So I think I need to write it with the minuses in there like that. And then I can just solve for the intersection of these two things. And I'll deal with the complex numbers later. Now, solving for the intersection of circles isn't that easy. I just chose to expand everything out and then just do this equation minus this equation. Or did I do this one minus this one? I can't remember. Let's find out. I think I must have done this one minus this one, because, yeah, this ends up being a plus 13. 4 minus 13 is minus 9, I believe. And then, sorry, minus 7? No. This ends up being a 13. And then you have 4 minus 13 is minus 9. Yeah, I said that right first time. And then, oh, and then this is a 23 over here. 23 minus, yeah. Anyway, take away this is this. I'm just waffling, aren't I? So you get this line. So essentially, wherever these two circles meet, they meet along this line, which you could, of course, rearrange to be this. But if you know that the two intersections, or the however many intersections you have, meet along this line, then you may as well just look for the intersections between this line and one of the other circles. So that's what I'm going to do. I'm going to substitute this x-coordinate into one of these circles, this one over here, and then just sort for that out, and I'll get my y-coordinates. So if we expand this out, we get this, and then we get this. Tidy it up, this goes into a calculator, obviously. You get this, you put that into, back into the line would be the best thing to do to get your x-coordinates, rather than back into the circles, put those two things back into there, and you'll get your x coordinates of this. So now we've got our two coordinates. We've got 4 over 17, 67 over 17, and the other coordinate is 4, 3. But of course, this is the point where, remember, we made up this Cartesian plane with x and y as we were originally looking at the complex plane. So we say the complex numbers of the intersection points are 4 plus 3i, and 4 over 17 plus 67 over 17i. Or you can factorize out the 17 and leave it like that. Okay, good. Question number 3 then. So we've got a second order differential equation here. So what we do is we ignore the 26 for now, turn it into a homogeneous one. Looks a bit like this. And this is the auxiliary equation, of course, replacing these with m's and m squared. Solve this in a calculator. Obviously, you just get this. Now that's two complex roots, so we need to remember what case we're in for the solution, what the solutions look like, and it's going to be e to this t. So it's going to be e to the minus 0.3 t at the front, and then it's a cos this t plus b sine this number t as well. And that's the general solution there-ish, except I haven't sorted out the 26 yet. Because 26 is just a constant, we replace x with lambda, and we say, okay, well, if we put lambda into here, if you differentiate lambda once or even twice, it's obviously just 0. So we get 13 lambda equals 26 left over. Lambda is 2, and then you just shove the 2 on the end there. And that's our 4 marks for that. Now, initially, there are no antibodies in the bloodstream. So when t is 0, x is 0. And also, the concentration is increasing at 10. So dx by dt is 10. And we're supposed to use these initial conditions to find some other stuff. Now, of course, that's usually initial conditions to solve for a and b first. So let's put in t is 0 and x is 0 into here. And you get this, which means a is minus 2, because, of course, sine goes away when you put 0 into it. So that's great. And now that doesn't help me find b, though. So what I have to do, I think, is I have to differentiate this equation in order to make this useful. So differentiate this, use some product rule. This differentiates to minus 0.3t to the power minus 0.3t, and then you leave this one alone. And then you differentiate this and leave this one alone, which is what I've done here. Cos differentiates to minus sine, remember, sine differentiates to cos, and you bring out these 0.2s. And now we can use dx by dt as 10. Of course, this 2 differentiates away. Use dx by dt as 10 in here, substitute in t as 0 again. When t is 0, that just goes to 1. This goes to 0, that's 1. This goes to 0, and we just end up with a bunch of b's, I think. What is this line? Have I just written out exactly the same thing again? No, I've substituted in the a value I had, of course. Yeah, I substituted in the a value that I had of minus 2. And now I can substitute in these boundary conditions. And I solve for b, and it's going to be equal to 47. So that's good. I got a is minus 2, b is 47. So let's update our solution here. And we get this solution here, which is cool. Just written it up here, I think. And now, okay, find the maximum concentration of antibodies. So maximum concentration. So I think I need to differentiate this, which I just did, so that's okay. But this time I have a and b. And I need to set this to be 0 to find a maximum point in it. Okay, and now, of course, this is never 0, so I can just times everything out by this to get rid of it. And I can also, once I've done that, once I've got rid of these e to the minus 0.3 t's, I can group together, or I can expand out this 0.3 out into these two, and then just collect these, and then I can collect the sines and causes together. So this looks complicated, but I haven't really done very much. I've just got rid of these two bits, expanded out this minus 0.3 to make this, and then just kept that one the same, and then moved together these sines and causes. And now, of course, I can just move the sines to the other side, divide by 13.7, divide by cos 0.2t, and we get tan 0.2t is 10 over 13.7. Do inverse tan on that, and then times it by 5 to get t is 3.15. Now, that's the time when we have maximum concentration. I haven't proved it's a maximum. Maybe I should have done that. Okay, for now I'll say that's the time when we have maximum concentration, and what I need to do is I need to substitute that time back into my x, my formula for x, and I'll find x is this. Now I'm just thinking I probably could and should have proved that was a maximum concentration. I'm wondering if there's any cheap way of avoiding having to do that, but the safest way, of course, would be to differentiate this again, substitute in this value for t, and just show that it was less than 0. So I'll just say out loud right now, I'm not going to change or edit this, I'm just going to say out loud, maybe you should have done that, just to justify that it was maximum. But in any case, that's the value there. And then the last part says that they want to give a second dose of this vaccine. Of course, we didn't talk in any way about what this was about, but it's about vaccines, very topical. Anyway, you're allowed a second dose of vaccine as long as your antibodies have dropped below this figure. can you do it at 10 weeks after this? Well, this is very simple. You just shove 10 into here and show, yeah, it's less than 5, so sure, they can have a second dose. Cool, that's it. Question number 3, so lovely de Moivre's question here, very straightforward. We just used de Moivre's theorem, which is this. Technically, I should have put an r to the n here, but I can't be bothered. I'm just going to run with this because we don't need it. Of course, you can use binomial expansion on this part. You put in 7, obviously. You can use binomial expansion on this part here to find this. So I know I've done it very quickly, but this is 7 choose 1, this is 7 choose 2, 7 choose 3, 7 choose 4, 7 choose 5, 6, and 7. And now the i's, when you take 1 I sine theta, you have an I. When you take 2, I squared is minus 1, so we have a minus. When you take 3, you have minus I. When you take 4, that's I to the 4 is I squared times I squared, which is minus 1 times minus 1, so you just have a positive with no i's, and so on. So it kind of alternates like this with some nice little patterns here. But of course, this thing here is equal to this thing here by de Moivre's theorem, so we can say that. But of course, if this thing is equal to this thing, then whatever has an I attached to it must be equal to all the things that have i's attached to them, and whatever doesn't is equal to whatever doesn't. So this I sine 7 theta must be equal to just the terms that have I in them, which are those 4 terms there. Of course, we can just divide everything by I here to get rid of them entirely, and now we're on the right tracks here, but the thing that they want only has signs in it. So we're going to use, of course, cos squared equals 1 minus sine squared. Now, cos to the 6 is essentially cos squared cubed. So this here is 1 minus sine squared cubed. And this here is 1 minus sine squared squared, and this is just 1 minus sine squared. And if you expand this out and expand this out, you get this. Apologies for the terrible double line thing, it's just that there's not enough space here. Then you just keep expanding. I'm not doing anything intelligent here, I'm just expanding, and then I'm just tidying up, and you pray that you haven't made a mistake, and it matches, and it does, that's good. Next part of the question was hence solve this. Now, of course, we should see the similarity between that and that here. So let's just let x equal sine theta, and then we get 1 plus all of this, which we know to be sine 7 theta, equals 0. Which of course means take away 1, and you get this, do sine inverse of that. Now you can work in degrees or radians here. I worked in radians. I found the first 4 solutions that you run into if you search left and right. So if you go right into the positives, you obviously get 3 pi over 2, and then 2 pi along is another 7 pi over 2. Or you go into the negatives and you get minus pi over 2, and then another 2 pi along gets you to this. And those are the 4 solutions there that I found. Now the thing is, and I don't 100% understand why this is the case, I more don't understand how you're supposed to know this. But if you just keep solving this, so obviously divide this by 7 and then put these values here into there, you get these 4 values. And now, of course, this is a degree 7 polynomial, so it could have up to 7 solutions, right? Now it only has 4 distinct ones here, and I don't really understand how you were supposed to know that it was only supposed to have 4. The thing is, when you write down, so I did this, I put down 11 pi over 2 and so on, 15 pi over 2, and then going backwards, minus 9 pi over 2 and minus 13 pi over 2 and so on. But when you then divide those by 7 and put them in here, you just end up with repeats of these 4 things. You can't get any other answers other than just repeats of these, and I'm not really sure how you were just supposed to know that, or whether you're supposed to just do what I did and just try more of them and realize that these are the only 4 that ever come up. Anyway, people can enlighten me in the comments, I'm sure. So question number 5. Yeah, this is just saying what I said out loud. Question number 5. So we obviously inverse tan both sides to get this, and then we can differentiate this implicitly. So x differentiates to 1, tan y differentiates to sec squared y times dy by dx, because you've differentiated with respect to x. And then just divide by sec squared. Sec squared, according to a formula that's, I think, in the formula book, otherwise that you should probably just know, is this. So you put that in, and then tan squared of y is just x squared. So it's just 1 over 1 plus x squared. Good, so that's nice, easy, 3 marks. Then we have this slightly different function, which is very similar, but it's got an x in front and a 4 here. And you're shown the integral of it. So, okay, well, obviously this is going to be helpful here that we've just done. So we're going to integrate, I've just moved some stuff away there. We've learnt this from the first part. So I'm going to integrate this, of course. Now, I'm thinking immediately that since they just showed me how to differentiate this one, I'm thinking integral by parts immediately, because in integration by parts, you integrate one of them, essentially, and differentiate the other one. So I'm thinking that's probably what they were essentially leading me towards doing. So, okay, firstly, I just need to double check what the differential of this is, because it's not obvious how it transforms to this one. And if you just shove a 4 here, because there's a 4 there, you would be wrong. So let's just double check. So set up the same thing, differentiate implicitly, divide by sec squared, replace it with 1 plus tan squared. Now, tan squared is actually 16x squared. So we end up with this as the differential. So I'm glad that I checked that. It is slightly different, but we've got this as our answer. So okay, we do integration by parts. So integrate this one, which is obviously just x squared over 2, and then leave this one alone. And that's my first bit. And then take away the integral of still integrating the first one and differentiating that one, which gives me this. I know I just did that in a way that most people don't, but all I do is integrate the one I can integrate, times by the other one, and then take away integral of still this one integrated, differential of the other one. That's how I think of it in my head. Okay, so this obviously there's a little bit of cancelling here, and you get this. And now I think this is the toughest part of the whole thing, is working out how to integrate this bit here. It's not easy at all. It took quite a bit of staring on my part to do this, but eventually I started looking through the formula book for integrals of this type and realized that probably what I want to do, and also I started looking up here and was thinking, okay, well, how do I get this out? How do I just get a regular, like this bit matches perfectly, right? How do you just get a regular x out of this? Like, how are you going to do that? Well, the way that I eventually figured out is you can split this into 2 fractions, not by partial fractions or anything like that. Actually a bit simpler, you can split it into something that looks a bit like this. Because, of course, if you combine these, you get this thing times 1 at the top here, makes 1 plus 16x squared minus 1, so the 1's cancel, you just get 16x squared. And then this denominator obviously stays the same. But of course, that gives you a 16x squared on top if you combine these, which I don't have. I want an eighth of that, so I'll just shove an eighth there. And the reason that I thought of this is mostly because of this term. And because this looks much more like something that's integrable from the formula book. So this seems like a good step. Of course, I can integrate these 2 bits separately. I can just integrate this bit and then this bit alone. This is obviously super easy to integrate. Now this isn't, but it does look just about like something I can do. If I factorize out of 16 from the bottom bit to make this, and then obviously I can just move the 16 out here. I've integrated this bit, notice, because it was super easy. Now, what I've done here is I've taken out the 16 to just times by 8 to make there. And then here, this is 1 over 4 squared. And the reason I've written it like this is because now I can finally use this thing, which I was eyeing up the whole time. But now I've perfectly got 1 over something squared plus x squared, which I know integrates to this, which is something of the form that I have here, which is good. So, okay, I can just use a as a quarter. In this formula here, 1 over a quarter is 4, x over a quarter is 4x, so that's perfect. And then just times the 4 out here, and we end up with this, plus k, because of course at some point when I integrated I needed a plus constant, and I think we end up with exactly this, with a being these, a, b, and c being these numbers here. So yeah, I'm done with that. Good. Hence find the mean value. So you just need to know the mean value formula. This bit's very easy as long as you remember it. It's this formula here, integrate it between here, and then just do 1 over this minus this at the front. It's essentially exactly what it sounds like. It's a mean value. You're working out the mean of the function by doing this. So that's cool. Apologies for this 0 hanging out down here. I couldn't get it to go up there. Of course, I've just replaced this integral of fx with what I just found. You just shove these things in here, and then divide by that. I'm not going to go over it in much detail. You just get this. Good. So 2 questions to go, I think. An interesting matrix question here. It actually asks you to invert a matrix by hand here because they've got a k here, so you can't just put it in a calculator. So okay, inversing this by hand then. So first we need to work out the determinant of this matrix. So it's k times the determinant of these 4, which is -1, -1, so that's minus 2k. And then it's minus 5, because when you're in this one you do a minus, times the determinant of these 4, 1, 2, 1, -1. That's -1, -2. And then plus 7 times the determinant of these 4, so that's 1, -2 there. And we get this. That's the first step. Second step is to transpose this matrix here. So you write, this is the first column instead. This is the second column. This is the third column. That's the transpose. Then you replace every single entry with the determinant of the 4 figures that are... Okay, so you replace this k. If you imagine drawing a line, this is how I was taught it, down here and here, because that's where k is, a line there and there. The only 4 numbers left of these 4, you work out the determinant of these 4, and then you shove it there instead. So -1, -1 gives you a -2 there. And then for this one, you cross out this line, and you work out the determinant of 5, 7, 1, and -1. So that's -5, -7, and you put a -12 there, and so on. And you just do that for every single one. And that's called the minor matrix, I think. Then you times that by this picture. So you times this entry by a plus, so that doesn't do anything. But you flip the signs on those four, essentially, is all that happens here, is you flip this sign, this sign, this sign, and this sign to give you this. And then the very last step, I believe, is to take this matrix and times it by 1 over the determinant, and you end up with your inverse matrix. Good. So, hope we know that. Find you don't have to do that very often, thankfully. Find in terms of P the coordinates of the points where this intersect. So there's probably some more intelligent things to do, but I mean, obviously first you say this matrix here is identical to this one as long as k is 2. Like I could write this in this form, and I have the same matrix as long as k is 2. And of course I can solve this by just front multiplying both sides by the inverse matrix. Now this looks obviously horrific, but of course this m inverse times m is just 1, so I just get this on this side. This is of course just 1 over 4, and then I can just multiply it by all this. I've simplified this up as well, obviously replacing k with 2 because that's what we need to do. And we get this, and of course we can just multiply these two things out. This times 1, this times p, this times this line, and then this line times this is this line, and so on, and then just divide everything by 4 if you want to. Obviously simplify this up, and I think I was being a bit extra when I wrote this, but essentially x is just the top bit, y is the middle bit, z is the bottom bit, and you get these three things here. Good, so the last bit then, find the value of q for which these intersect a straight line. Now, okay, they've replaced k with 4, and we notice if k is 4, then this is 1 over 0. So this, I believe, is called a, what was it called? I can't remember the names of anything, because I don't have to do this that often. It's non-singular, isn't it? It's non-singular when the matrix has a determinant, when you have a 0 here. Non-singular, but we have to figure out whether it's continuous. Now it's not continuous, consistent. Now it's telling us it is consistent because it's saying it's a straight line. So what I can do is I can say, well, okay, if it's consistent, then let's eliminate one of these variables. So if I do 7 lots of this one, the middle one, take away the top one, I get 3x plus 2y, nothing, 7q minus 1. Right, that's 7 lots of this minus this. And then if I do this one, say, I think I did this one plus this one, did I? 2 plus 3? Yeah, this one plus this one gives me this. And now we have the same 3x plus 2y here. But if they meet in a straight line, that means the situation is consistent, which means that this thing must be equal to this thing, because they've told us this is a consistent equation. So this number must be equal to that number, which makes q a half. So we've solved for q as a half. Now, for this value of q, determine a vector equation for the line of intersection. So these meet at a line, they're asking us for the vector equation of it. Now, the easiest way to work out the vector equation of a line is to just find 2 points on that line. But of course, a line goes through x, y, z. You can just choose one of those things to be 0 and find the other 2 points quite easily, because if I have q as a half, this is 2.5. If x is 0, then that means that 2y equals 2.5 and y equals 5 over 4, right, or something like that, 1.25. And then likewise, I can just find z very easily by using any of these equations here, and I'll find z is this. So I've got a point on the line here. And I'm allowed to do this because, of course, a line is going to go through some point when x is 0. And for the same reason, I can find another point by just saying, well, it must go through somewhere where y is 0. And when y is 0, you put 0 into here. This is still 2.5. You divide by 3 to get 5 over 6, because it was 5 over 2, so now it's 5 over 6. Then you put in z. From these equations, you just find z very easily, and you get another coordinate. And the easiest way to find the equation of a line now is to say, well, the equation of a line in vector form is just any point that you want, so I can use either of these two, plus lambda, the direction, or essentially the vector to get from one point to another. So to get from, say, this point to this one, I need to add 5 over 6 in the x, I need to take away 5 over 4 in the y, and I need to, I can't remember what that is, but you just do this minus this, which actually ends up being this, plus 3 over 4, which gets this, and then the vector form of the line is this. So you just choose any point that you want that you know is on the line, plus lambda, the direction vector being how much you need to get from one point to another, and we end up with this vector equation here. And we only have one question left. It's actually, I thought, probably one of the easiest questions on the paper. It looks horrible, but it's the last question, so it's always intimidating. But it's actually very straightforward, I think. Point A has coordinates this and B this, so you just shove those into here, and you end up with a nice simultaneous equation in A and B, which is super easy to solve, and you just get that B and A are those two things, so that's really nothing to write home about. You just pick up 2 free marks there, which is nice. Curve C2 is modeled to be an arc of a circle, center 0, 3 there. Use calculus to determine the volume of all of this. Now you obviously want to break this up into 3 bits. You want the bottom bit, which we can actually see is just going to be a cylinder around the bottom here. And now this distance is just going to be 1 because of this point here at A, and the height is going to be 0.5. So this cylinder is pi r squared, r being 1 for the area of the face on the bottom, times by 0.5. So it's just pi times 1 squared times by 0.5, which is pi over 2. So this volume up to this straight line here is pi over 2. Then we work out the volume of this section between A and B, which is going to be pi times the integral of x squared, because we're going to rotate this around the y-axis is the plan. So pi integral of x squared between the y-coordinate of A and the y-coordinate of B. Now, x squared is just a squared over y plus b squared, and we know A and B, so we just put those in between 0.5 and 2.5, as I said, with pi on the outside. Now this looks scary to integrate, but actually you realize it's very easy when you just take out the 4 and then realize that it literally just integrates to -1 with a -1 in front, because the derivative of this is just 1, so you can just do that. And then you just shove in the 2 limits, and you eventually end up with this, which is nice. So what we've got so far is that this cylinder on the bottom is pi over 2, this thing up here is pi, this bit, and now we just need to figure out this bit of the circle up here. Now they told us the center was 0, 3, so I think I can work out the radiuses of this circle, because this point is 0.5, 2.5, so it's 0.5 across, 0.5 up from 2.5 to 3, and then I can just do Pythagoras, half squared plus half squared, or I could just remember the 1, 1 root 2 triangle, and this is half of that, so this distance must be root 2 over 2. So that's cool. So the equation of it is this, center 0, 3. Radius squared is actually just a half because it's 2 over 4, so radius squared is just a half. But of course my plan here is to integrate, or pi integral of x squared again, between 2.5 and this top point here, which I need to work out. But it's just going to be 3 plus root 2 over 2, because that's the radius. So, I actually wrote it as 1 over root 2 at this point because I was being anarchistic about this, but whatever. So this is a mixed number, even though it's absolutely hilarious. This is 3 plus 1 over root 2. It's a mixed number. It's just, yeah. And then x squared is just this, obviously, so that's good. And then I got the pi on the outside. I just need to integrate this, which again, it turns out to be quite easy. And then you can use the calculator to shove these things in, and you eventually get this. And so, of course, we just need to add that to pi over 2 and pi. This is 3 pi over 2, and then this is, I guess, 36 over 24. Add 5 is 41 over 24, and we'll end up with our final answer in exact form. And I think that's the entire paper, so thank you so much for watching, and I will see you next time.